All right, so today we're going to look at discussion 2-2, D block elements. All right, so why are D block elements unique? Well, they're unique for a number of different reasons. The first of which is that they have multiple oxidation states that will lead to partially filled d orbitals. Now remember, what we mean by oxidation state is charges. So they form ions with multiple different charges. Secondly, they'll form colored compounds. They will display catalytic properties, and they display magnetic properties. All right, so variable oxidation states. What I want you guys to do now is write the electron configurations for vanadium, iron, and nickel. Now, we learned how to do this in IB Chem 1, and it was reviewed in the pre-Unit 2 podcast. So if you haven't watched that podcast yet, you really should do that. Now, you can do the shorthand or full configuration if you want. It is fully up to you. So pause the video and go ahead and write those configurations. Okay, so for vanadium, we see that vanadium has the full electron configuration of argon, as well as 2 electrons in the 4s and 3 electrons in the 3d. So if we look at vanadium, we see its element number 23. It has the full electron configuration all the way up to argon, as well as 2 in the 4s and 1, 2, 3 in the 3d. Alright, so iron has argon 4s2 3d6, and nickel has argon 4s2 3d9. So my question is, are these considered true transition metals? Well, if we look at vanadium, it has 3 electrons in the 3d. If we remember Hund's rule, which says that electrons will only fill orbitals one at a time, and no one orbital within a sublevel will have a pair of electrons in it until all the orbitals have at least one. So that means that vanadium will show 3 unpaired electrons in its d sublevel. Iron will have 4. It'll have 1 set of paired and 4 unpaired electrons, and nickel has 1. So what oxidation state do you predict that all of these would have? Well, it's important to remember that when a metal is ionized, the first electrons to be removed from the atom are in the valence shell. Now, we see in this electron configuration, we have electrons occupying the 4th energy level and electrons occupying the 3rd energy level. So it seems to me that all of these metals can lose 2 electrons, which would give them a charge of +2. Now, since they will always lose those 4 electrons first, that means that all, or I should say most, of the D block elements will have an oxidation state of +2. All right, so there are a couple interesting exceptions that you're required to know. It's copper and chromium. So we see that copper has the full configuration of argon and then 10 electrons in the 3d and 1 in the 4s. And chromium has 5 in the 3d and 1 in the 4s. And the reason that happens is because it is more energetically favorable. So if we look at our periodic table, we'll see that copper is in the 9th spot in the 3d. So we would expect its electron configuration to be 4s2 3d9. But instead, it is not. The reason is because it is a more stable configuration for copper to have a full D sublevel and a half-filled S sublevel than it is to have a partially filled D sublevel. And that actually explains the presence of the copper 1 ion, because copper can simply lose that 1 4s electron and then have a full stable 3d. Now, zinc and the members of its group are not considered to be transition metals, right? Because they only have 1 oxidation state, and in that oxidation state, they will have completely full d orbitals. We see zinc and the members of its group here are in the 10th spot in the 3d. So once it loses those 2 4s electrons, it will have a 3d sublevel, which doesn't like to be broken up. Okay, so magnetism. There's 2 different kinds of magnetism that we see in D block elements, paramagnetic and diamagnetic. Paramagnetic elements contain unpaired electrons, and those unpaired electrons act as tiny little magnets. And that means that their relationship with an external magnetic field will be one of attraction. And diamagnetic elements contain only paired electrons, so they will be repelled by an external magnetic field. So what kind of compounds do d-block elements make? Well, they make two different kinds of compounds. One is ionic compounds that we're used to seeing. So examples of that would be copper 2 oxide or iron 3 chloride. The definition of ionic bonding in that sense is electrostatic attraction between oppositely charged ions. Now that is not a true bond in the sense of the word because it is not formed by the sharing of electrons. D-block elements can also form coordination compounds. Now, in a coordination compound, a ligand will form a coordinate bond with a positive metal ion, which is a true bond in the sense of the word because we're talking about the sharing of electrons. So you're probably wondering what is a coordinate bond and what is a ligand? So in a coordination compound, the type of bonding is coordinate bonding. Now, in coordinate bonding, one species will provide both of the bonding electrons. In a standard covalent bond, one species will contribute one electron to the bond, and the other species participating in the bond will supply the other. But in coordinate bonding, one species, in this case the ligand, will donate both of the electrons to the bond. And a ligand is an atom or molecule or ion that contains at least one pair of electrons. Now that makes a lot of sense because in order to form a coordinate bond, you need to have at least two electrons, a pair of electrons. So common ligands that we see, first of all, there's two types of ligands, monodentate and polydentate. Monodentate ligands are ligands that can only bond to the metal cation in one spot. And they include halide ions, hydroxide ions, cyanide ions, water, or ammonia. And then polydentate ligands are ligands that can bind to the metal in more than one place. An example of a polydentate ligand is EDTA. So one thing you have to do is figure out the oxidation number of the transition metal cation in a coordination compound. And actually that's pretty easy to do. First thing you do is look at the overall charge on the compound. The compound we see this one has an overall charge of +2. The next thing we do is subtract the charges of all the charged ligands. Now charged is underlined there because if a ligand does not have a charge, like water, then it will not factor into the charge of the overall compound. So for this first example, we see that the charge on the whole complex is +2, and from that we'll subtract all the charges of the charged ligand. Well, water does not have a charge, so it just is +2 minus 0, which tells us that copper in this complex has a charge of +2. In the next example, our ligand is chloride ions, and there are 4 of them. So we know that if you have 4 chloride ions, they will be supplying a negative charge of -4 to the complex. So we'll take the overall charge of the complex, -2, and subtract from it all the charges of the charged ligand. So -4 tells us that iron in this case is +2. Okay, so why do transition metals make colored compounds? So you probably recall from IB Chem 1 and the pre-Unit 2 podcast that the D sublevel contains 5 orbitals. Well, what happens when a ligand bonds to the coordination complex? It causes the ligands, or the orbitals to split in 2 different energy states. Now, the reason that happens is because 3 of the orbitals in the D sublevel are aligned to the XYZ Cartesian plane. So the lobes of those orbitals do not interact with each other, and there's very little electron-electron repulsion. But the other 2 lobes, the dx squared and the dx squared minus y squared, overlap with the other 3 orbitals. So when the ligand bonds, it causes additional electron-electron repulsion, which causes the orbitals to move away. So what happens is that electrons in the lower energy levels will absorb discrete wavelengths of light when they move up to a higher energy level. Now when they move back down to a lower energy level, they will emit a certain wavelength of light. Now the wavelength of light that is emitted is complementary to the wavelength of light that is absorbed. So if a transition metal complex absorbs red light, which is a low energy light, it will emit a higher energy of light. So there are three factors that can affect the amount of splitting that we see between those d orbitals. One is the identity of the metal ion, two is the charge of the metal ion, and the third is the identity of the ligand. So let's look at those one at a time. So effect of the metal ion. So metal ions with more protons will result in smaller splitting. As the charge of the nucleus increases, it will have a greater attraction, to all of the electrons in the atom. So it will pull all the sublevels and all the orbitals closer together. Now, it's important that we control for oxidation state, because if we're looking at different metal ions with different oxidation states, it introduces a new factor which complicates things a little bit. So if we look at iron 2 versus copper 2 would have a smaller splitting, which means than iron 2, which means it would absorb a lower energy of light. So we look here, iron and copper, we see that copper has a more greater charge in the nucleus, so it will have a smaller splitting. Oops. All right, and then also oxidation state. So for a given metal, a greater oxidation state will mean greater splitting. And that happens because as the oxidation number increases, it means that the nucleus, or the cation, I should say, is more positive. So it'll have greater attraction to all of the electrons and pulls them closer together. Well, when you pull the electrons closer together, that actually increases the electron-electron repulsion, which will increase the amount of splitting. So copper 2 will have a greater splitting effect than copper 1. And finally, the effect of the ligand. So some ligands are considered weak field ligands and some are considered strong field ligands. And we can look at what is known as a spectrochemical series. The spectrochemical series is a spectrum that shows all the ligands we're going to be dealing with in this class from weak field to strong field. So iodide is the weakest ligand and cyanide ion or carbon monoxide are the strongest. So if a So weak ligands will give less splitting than strong. So if a stronger field ligand bonds to a metal, what would you expect to see in terms of the shift in color? So pause the video and think about that for a second, and I'll give you the answer in a second. All right, so we have to look at the color wheel. A stronger field ligand will give you a greater amount of splitting, which means that a higher energy light will be absorbed. And since the complementary color is transmitted, that means that a lower energy light will be transmitted, right? So closer to red than violet. So here is our color wheel, and if we look at any one color on the color wheel, we see that the complementary color to the color we're looking at is the color exactly on the opposite side of the color wheel. So for blue, the complementary color is orange. For green, the complementary color is red. So if a compound, or a coordination complex, I should say, absorbs green light, then it will appear to us as red. So if a compound appears blue, what color light will it absorb? Well, that would be orange light, between 647 and 585 nanometers. And what would be the approximate wavelength of light absorbed by a green compound? Now remember, if the compound is green, that means green is being emitted, which means that red is being absorbed. So we would see the wavelength somewhere between 647 and 700 nanometers. And that is all for discussion 2-2. Thank you so much for watching.